Okay.
Happy day, everyone. This is Orekoya Olusegun, Physics Mathematics Fundamental on YouTube. In continuation, as regards sound wave, I derived the necessary expression or equations that we need to solve simple exercises on wave, sound wave through open pipe. Please do check on my last video if you are interested in the derivation of the formula I'm going to use to solve an exercise. So today we are going to solve an exercise under sound wave in open pipe. Now this is the exercise we are going to solve. I will read. An organ pipe is 0.85 meter long. The pipe is open at both ends. The first question says find its fundamental frequency at 15 degrees Celsius. Find the frequency of the fourth harmonic. Question 6 says determine the frequency of the fifth overtone. Then the next one says what is the wavelength of the second overtone. This is a very simple question. Now let's start. An open organ, because the organ is open at both ends, the length of that organ, length L, is given as 0.85 meter. Now the pipe is open at both ends. These are the ends that the pipe is open. Now they said find its fundamental frequency at 15 degrees Celsius. When sound wave is sent into this pipe, the temperature of the air, this is the sound wave. The sound wave is passing through air, through the assistance of the air particles, and the temperature of the air, according to this question, is 15 degrees Celsius. 15 degrees Celsius. So, and then the velocity v of sound wave under a given temperature is given as 331 plus 0.6 T, where T is the temperature in degrees Celsius. So since the sound wave is being sent at this temperature, I will substitute here to get the velocity of the sound wave. So V will now be 331 plus 0.6 T. Our T now is 15 degrees Celsius. So using your calculator to evaluate this, we are going to have 340 meter per second. So that means the speed of this sound wave into this pipe is 340 meter per second. Now, because we are having an open pipe, the formula we use for the open pipe is given as NV is equal to LFL. NV is equal to LFL. Now, where N is the number of harmonic of the wave, and L is the length of open pipe, and then Fn that I have here is the nth harmonic. Now the first question says find its fundamental frequency. From this expression, Mv is equal to L F subscript n. For the fundamental frequency, the value of the harmonic is 1, that is n is 1. So I have 1 times v is equal to the length of this pipe is 0.85 f1, and the speed of sound that we calculated the other time is 340. So I have 340 divided by 0.85 will give us first harmonic. Using our calculator, the first harmonic F1 is 200 Hz. So the first harmonic is 200 Hz. That has solved the first question that we have here. Then the second one says we should find the frequency of the fourth harmonic. Fourth harmonic frequency is given as F4. That means our N is 4. So we go back to this equation that we have here. We put 4 times this speed of sound or the velocity of sound wave. Then it's equal to length of the pipe 0.85 times F4. That is 4 times the V is 340 times 0.85 times F4. Dividing both sides by 0.85, the fourth harmonic now will be 4 times 340 divided by 0.85. So pressing the calculator, we have 800 Hz. That's the frequency of the fourth harmonic. Now, the next question says we should determine the frequency of the fifth overtone. To be able to get overtone, you know, if you have harmonic, the set of harmonic for open pipe is given as n to be 1, 2, 3, 4, 5. For the subsequent overtone, for the first harmonic there is no overtone, we put 0. So we have 1, 2, 3, 4, and so on and so forth. So when we talk about fifth overtone, my fifth overtone is not here. I can write it as 5 here. Then I can look at the number of harmonic for the fifth. This is 1, 2, 3, 4, 5, then 6. So we can see that for the first harmonic, there is no overtone. For the second harmonic, the overtone is 1. For the third harmonic, the overtone is 2. So for the fifth harmonic, for the fifth overtone that we have here, the harmonic is 6. So we are going to use F6 in calculating the fifth overtone. So in our formula, MV is equal to LFN. And now the number of harmonic is 6 times the velocity of sound wave is equal to length of the pipe that we have here is 0.85. Then F subscript 6. That is the fifth harmonic. So when we make F subscript 6 the subject of formula, we have 6 times 340 divided by 0.85. Pressing the calculator, we are going to have 1200 Hz as our answer. So the sixth harmonic is the same thing as the fifth overtone. Now the next question says that what is the wavelength of the second overtone? Like I said, if you look at this place now, the second overtone corresponds to the third harmonic. So second overtone corresponds to F3. Now, to find the wavelength of the second overtone, in which second overtone corresponds to the third harmonic, what we are going to do is to use this relationship. The velocity of sound is given as the wavelength times frequency, but our frequency here now is 3. So the wavelength of the third harmonic, which is also equivalent to the second overtone, can be written as wavelength subscript 3. So when we make wavelength subscript 3 solve a formula, which is the wavelength of the second overtone, we are going to have the velocity of the sound wave divided by the frequency, the third harmonic frequency. So how do we get the third harmonic frequency? We can quickly get that relationship using I think NF, okay, Fn is equal to N times first harmonic. So F3 can be obtained as 3 times first harmonic that we got the other time. That is F1 that we got the other time. I think 2000. So times 2000 here. So F3 is 3 times 2, that's 600 Hz. So we can equally use the formula, this formula, to get our F3. We can either use this formula to get our F3, or we use this formula also to get our f3. In this case, the substitute n here is 3 and the coefficient n here is also 3. We make f1 solve the formula. So going back here now, our f3 will be 600 and the velocity at the temperature of 15 degrees Celsius that I calculated the other time is 340. So it's going to be 340 divided by f3. Our f3 is 600 hours. So we have over 600 hours, which is the wavelength of the second overtone. So dividing this with our calculator, 340 divided by 600. It's giving me 0.57 meter, which is also equivalent to 57 centimeter. So I believe that we are able to understand one or two things concerning how to solve exercise relating to the sound wave in open pipe. In my other video, I'm also going to derive the necessary formula as well as solving a problem involving transmission of a sound wave through string and transmission of sound wave through closed pipe. Before I go, please do not forget to share, like, subscribe and click on notifications button to be able to have more of my video. Have a nice day. Bye.